Perfect. Okay, so thank you all very much for joining the One World seminar series on the mathematics of machine learning. Uh, this is my great pleasure to introduce Qing Ku from the University of Michigan. Qing is a professor of electrical engineering and computer science, and he's been working in doing a lot of very interesting work at the intersection of machine learning from a foundational perspective, also looking at related topics of how to understand some of these methods from an optimization perspective, from a signal and image processing perspective, and more recently has been looking at all this specifically for deep generative models. And so today it's my pleasure to have Ching with us and to be speaking to us about understanding generalization of deep generative models. I'll mention that if you have any questions during the talk, feel free to put them in the chat, and we'll also have some time towards the end to both answer those if we don't have a chance during the talk or um, afterwards during the Q&A. So, Ching, please take it away.
Yeah, thanks so much, Ricardo. Yeah, it's really nice having me. I mean, it's really honored to be here. Uh, so today I'm going to talk about something I've been working on roughly around 3 years. So we're trying to initially we find some very interesting phenomena, and then actually this we later realize that actually it strongly relates to this kind of very interesting generalization phenomenon, especially in diffusion and this type of generative models. And so in the first 10 minutes, I want to give you a quick like overview of what is diffusion models and if you don't know about this, and then I will go into the phenomenon we find and some mathematical theory we are trying to develop and followed by certain some applications. So I think in the past 5 years, right, we are witnessing the tremendous growth of generative AI models, either in language or vision, right? In language, it starts from the transformer BERT model, and more recently we have all kinds of large language models. Is really powerful. On the other hand, for image and video generation, so in vision. I mean, this is start actually 12 years ago from VE and GAN type of models. But those models have some limitations, and more recently, the diffusion models kicks off, right? And we have this kind of text-to-image stable diffusion, and more recently, we witness this kind of video generation type of models like Vue, etc. So what is a generative model in general? So the basic idea of a generative model is that we want to learn some like say deep learning models or machine learning models. That the model is trained on the raw modality like raw images, audio, text, etc. Right? We're trained on one type of modality, but we don't have any labels. We just train with the raw data without a label. And once the model is trained, right, and then we're going to give the model a random input. And our hope is that we can generate some realistic images that is different from the training data, but they're realistic. And to achieve this goal, in the past, they start from the version autoencoder. And the autoencoder can be traced back to the early 90s. And the basic idea for version autoencoder is that, I mean, you have an input data X, where X is your input, and then you want to train the encoder to encode your data to a low-dimensional space to do data compression and representation learning. But I mean, to train such an encoder, you need to pair it with a decoder, such that you want to use decoder to reconstruct back the X. And later on, people find that actually, when you're training this encoder and decoder, not only the encoder is able to learn representations, but actually the decoder can serve as a generative model, right? You input some Gaussian noise, and actually the decoder can generate something realistic. But however, for this kind of one-step generation, because the versional autoencoder, we are doing the representation learning and the generative modeling at the same time. The VE actually is not doing very well in neither representation learning or generative modeling. The performance is not very good. And 1 year later, people introduced this kind of a GAN-based method. And this GAN-based method, the general adversarial networks, where we're trying to train a generator and discriminator at the same time, where the discriminator is trying to distinguish between real data, and the generator generates some fake images, and discriminator trying to distinguish between the real and fake. And and once the discriminator and generator is trained, right, so we'll use the generator as the generative model. But however, because we are training the generator and discriminator at the same time, often we are solving a minimax problem. And solving minimax problem actually is not very stable. And people show that actually it's very easy to run into some mode collapse issues where the model will generate something very similar images. And it's very hard to scale the training of a GAN model to larger data set. And that's why we run into this kind of issues when we're training the previous generation of generative models. So that's why later on, I mean, around 2021, and this diffusion model kicks off. And compared to the previous family of generative models, diffusion model is now trying to do one-step generation, right? So the previous VE and GAN type of models, right? You train a decoder or generator, and then you input a noise, it will do a one-step generation. But here the diffusion model is not aiming to do one-step generation. We're starting from a noise, right? They're trying to gradually remove the noise and to generate something realistic. And that's what, and actually, because of this, actually, if you look at the training loss of diffusion model, you're only solving a minimization problem that the training is much more stable. And you can easily scale up the training of diffusion model to larger data sets. And that's why actually it enables many powerful commercial and scientific applications like this text to image generation that you input some text, right? It can guide you to generate some realistic images. And recently people are also leveraging this idea of diffusion models to do language modeling, and we also see the recent success of video generation powered by transformer diffusion models. Moreover, people are also leveraging diffusion models as a prior to do all kinds of solving inverse problems, high-dimensional inverse problems. For example, for image restoration, data simulation, and a protein design, etc. So what exactly is diffusion models? Well, here I want just to give you a very quick review, and then we're going to go to the generalization problems which is a key focus of this talk. In simple terms, the diffusion models actually have two processes. One is a forward diffusion process, where you start from a clean image, and the forward diffusion process is gradually injecting the noise into the data until it achieves the pure noise. And mathematically, they can be captured by something as simple as the following equations, where alpha and beta are some predefined noise levels, noise schedules, and epsilon is a noise, is a Gaussian random noise. So basically, you're just gradually injecting the noise into the image until it completely corrupted to a pure Gaussian noise. And if you make this interval t to be and the intervals, time intervals to be very small, and this forward process actually can be described using a stochastic differential equation. So again, here f and g are some predefined noise scheduling. However, although the forward process seems quite trivial, the non-trivial part, the leveraging diffusion model for generation, is the reverse process. So actually, people show that this simple forward process actually can be reversed back uh, uh, through a reverse stochastic differential equation or SDE. And more recently, people show that actually the forward process can also be reversed through a backward probability flow ODE. That starting from the noise, you can following this backward ODE, and you can reverse this process to generate clean data. And this is how the generation of diffusion models actually works. But although this sounds nice, but there's a one caveat, is that if you want to enable this kind of reverse sampling for this backward flow ODE, you need to know the score function, right? So here, the score function is the standard score function, where you take the gradient of the log likelihood of the distribution at each noise level t, right? So when t equal to 0, this is a distribution of the clean images. So this is really a challenge, right? Even for the distribution of the clean image is not known, right? How can you know the noisy distribution at each different time step, right? So doesn't seem to, I mean, if we can estimate the score very well, actually we can enable the generation. But in practice, because we don't know the distribution of the data, the images, we don't have the score function ahead of time. And to deal with this issue, right, people are a naive and very intuitive idea is that why not we use neural networks to learn the score function from the data, right? So we know that neural networks, over parameterized neural networks are very powerful universal approximators, right? So why not we use a neural network to approximate the score, right? And this is the basic idea of diffusion models. And initially, if you look at the initial diffusion models and this task image stable diffusion, people are using this UNet-based architecture to approximate the score for each time step. And more recently, people are shifting to transformer-based models because people believe there's an underlying scaling law behind transformers and make the performance more predictable when we scaling the data size and the model parameters. And also, transformer better enable this kind of multimodal generation. So this is good, right? I mean, we can use neural networks to approximate the score. And once we approximate the score, then we can enable generation follow the backward ODE. And the remaining question is how can we train the neural network, right? We need to train the parameters. Need to learn the parameters of the neural network, theta. And the idea of learning such a neural network is that we need to design a loss function. And intuitively, the loss function should be that we minimize the distance between the output of the neural network and the score function, right? So basically, we want to do score matching. We want to minimize the distance between the score and the neural network output. As we mentioned earlier, right? So this vanilla objective function doesn't seem to be approachable because we don't know the score ahead of time. So this is something that we cannot optimize in practice. So instead, because we're injecting Gaussian noise, so we can leverage this Tweedie's formula. We can show that actually this population actually is equivalent in the following form, that right? So our neural network is equivalent, the score matching is equivalent to using our neural network to predict the noise. And so essentially, if the following loss function actually is something that we can optimize in practice, right? We can do an empirical approximation of this loss, and we can run stochastic gradient descent to minimize this loss in practice. And this is a purely minimization, right? Which means that training actually will be much more stable than GAN-based models. However, in theory, we want to minimize the population, right? But in practice, we are not going to able to do this because we don't know the underlying distribution of the data, we don't have infinite many samples, right? So what we do in practice when we training diffusion models is that we're going to train a finite number of images that is draw from the underlying distribution of our data, right? What we're going to do is that we're going to approximate the original loss with an empirical loss, right? We're going to minimize the loss where over a finite number of training samples, where xi is one training sample and n is the number of training samples. Then this is raises a question about generalization, right? Why we are learning on the empirical laws can enable generalization, that we can generate new samples, we can learn the underlying distribution of the data, right? So ideally, we want to minimize this population loss, but in practice, we are minimizing training over finite number of samples, right? There's a discrepancy between the population loss and the empirical loss, right? This could cause generalization error and potentially even memorization, right? So this is basically the question that I want to address in this talk is that when we're training our diffusion model on finite number of training samples, how close is the learned distribution induced by the model, where theta is the parameter of the neural network, and p theta is denoting the distribution we learn induced by our neural network learned to the true distribution, where the p data is the underlying distribution of our data, right? And here the challenge, there are two challenges. One challenge is that in real world setting, right, we don't know the true underlying distribution, right? How can we quantify the distance between those two? Another challenge is that we are, as I said earlier, we are training with finite number of samples, where we don't have infinite samples, we only have finite number n, and if you think about this, right, if your model capacity, if your neural network has infinite capacity, then actually neural network will just learning the empirical distribution of your data, right? So we'll just learn this kind of empirical distribution instead of learning the true data distribution, right? So why our model are not memorizing the training data and instead they can learn the true data distribution, right? This is a fundamental question about generalization. And in practice, if you do a deep investigation of this problem by looking at by fixing the model size and changing the size of the training data, you indeed observe there's a discrepancy, different phases in training, right? So you can observe where the central image showing you here is that where the x-axis is showing you the number of training samples where we are taking the log, where ID is the intrinsic dimension, which is fixed, where n is changing, and the model capacity is also fixed. And the y-axis is showing you the generalization score. I mean, the closer to 1, which means a stronger generalization, and closer to 0 means memorization. And what you observe that we're increasing the number of training samples from small to large, you observe this kind of a phase transitions from memorization to generalization. So on the left-hand side, when you have very limited samples, and in the memorization regime, what you observe is that your model will just memorizing the training samples. And this can be illustrated by the figure on the left, where the first row is the generated images by the trained model. And the second row is showing you the nearest neighbor in your training data set, right? You obviously observe that the generated sample is just a copy of the training data, right? This is a memorization. And this suggests that your model is just learning the empirical distribution of your training data. But however, when you increasing the size of the training data set, you observe that the model start to generalize, where it show on the figure on the right, right? The first row again is the generated images, where the second row is showing the nearest neighbor in the training data set. You can see that actually the generated images will be different from the nearest neighbor in your training data set. So, and then if you want to understand generalization, right, a very simple explanation of why this kind of generalization happens is that I mean, if your number of training samples increases, right? So if you make the n to go to infinity, then this empirical distribution eventually will approximate or interpolate the underlying distribution of your data, right? And if you want this approximation to be epsilon close, unfortunately, the number of training samples you need for this approximation to hold actually will grow exponentially in terms of the dimension of your data. So here, D is the number of pixels in your images, where D can be very, very large. So this suggests that if you just through this very simple argument, right, you will run into this curse of dimensionality, which is very common in high-dimensional learning problems, right? But however, if you look at what happens in practice, where diffusion model generalize, so the number of samples you need actually is not that large. So the number of samples actually is only around 10,000 or something, right? It's much less than the worst theory predicts. So then the question is that why there's a large sample complexity gap between the worst case theory predicts and what we observe in practice, right? So this is the fundamental question I want to address in this talk about generalization. So why diffusion models able to generalize? And to answer this question, so we partitioned the talk into three parts. So the first part, we're trying to better understand this kind of generalization phenomenon I showed here through through observation of this very interesting model reproducibility phenomenon. And based on that, we will try to develop a theory of generalization by looking into the low-dimensional structures of data. Actually, our model is not to learn arbitrary distributions, but we are learning on images. Images are relatively low-dimensional, and we are trying to precisely capture the sample complexity, why we can break the curse dimensionality when we're learning high-dimensional distributions. And finally, I want to discuss about, if I have extra time, I'll try to discuss about the relationship between generative modeling and representation learning. Actually, they are the two sides of the same coin under diffusion models. Finally, we'll conclude. First, I want to better motivate this problem through a phenomenon which I call it reproducibility. And specifically, I want to start with a question for all of you. And so the question actually I asked many times is that uh, so um, so the setup is the following, right? So far we have introduced the basic setup of diffusion models, and let's consider a setting as follows, where you have two diffusion models, where as theta one you consider is a parameterization of a UNet-based architecture, and as theta two is a transformer, where you train the two models with sufficiently many data points, but the data you trained for both models are the same. And once you train the two models, you're going to input the model with the same noise and follow the same ODE sampler. They're going to generate two images. And then my question is, uh, are the two images similar or dissimilar under such a setup?
Anyone feel free to to unmute. Maybe I'll say that if it's learning the same score function, and all the noises are the same, then you should get the same output, if they're really approximating the same underlying function.
Yes, yeah, exactly. Actually, this is something what we identified in practice is that when you train the models, I mean, they are learning the same scores. Actually, they're going to generate the same images. And this is why we call this a model reproducibility. And this indeed happens in practice. So what we visually find is that when you do experiment under such a setup, you're going to see that actually the diffusion models is able to generate almost the same images from the same random seed. And here in the results we showed here, so the first on the left is a U-Net-based model, where on the right is a transformer-based model, and in the middle is a different training loss where we use a consistent training loss. Where if you compare the different indices, so the same index across different blocks here is the same random noise seed, right? And you compare the same random noise seed, right? The generated images, even you are using different parameterization, different training losses, actually they are generating very similar images. And this is indeed true happens in practice across a lot of different setups when training the diffusion models. So that's why we call this a phenomenon, the model reproducibility, because the model seems to generate very similar images with the same input. And this is only a visual comparison, right? How can we quantitatively measure this? So to quantitatively study this phenomenon, so what we did is that we're going to measure this cosine similarity between the generated images. In other words, so sorry. Uh, so in other words, so suppose x1, x2 are the generated images from two different diffusion models, and we're going to measure the cosine similarity in representation space. We map the two images using the same image distributor into the latent space, and then we're going to compare the cosine similarity in the latent space to make it more robust. And if the cosine similarity is closer to one, then we see that this is a two images are very close to each other, right? Very similar to each other. If they are the cosine similarity is small, which means that actually they are dissimilar to each other. But however, this SSCD or this metric self-supervised copy detector is only measuring instance level. We only measure the sample level similarity, right? And what we want to do is that we want to measure the similarity between two models. And to do this, we introduce a probability measure. We're going to draw, like say, for many training samples, sorry, noise samples to approximate this probability where the generated samples is larger, the similarity of generated samples are larger than certain threshold. And you can imagine, right? So if this probability is closer to one, then the two models will be reproducing each other. So they will have a high reproducibility. And when the p is closer to zero, which means there's a minimal reproducibility. And in practice, we're going to approximate this probability by drawing random noise, many random noise, and take an average to approximate this probability. And then we show this kind of similarity matrix between different models with different random seed initialization for the weights. And actually, you can see that the minimum reproducibility actually is around 0.7. Is still very high, right? And we did even more comprehensive study between different models. And you can see that actually the reproducibility is still very high when we're doing such a very more comprehensive studies. However, when you repeat the same experiment on other type of generative models, like see if you do this experiment on GAN-based models and VE-based models, where you repeat this same setup with different architectures for GANs, for example, actually there's almost zero reproducibility between the models. But it seems to be very a prevalent phenomenon in diffusion models, right? So my conjecture is that the GAN and VE models actually they are not learn very well. They are not truly approximating the distribution, and actually they don't have such a reproducibility phenomena. And our findings actually is complementary to recent work by Steven Malad and Eros Simoseli's group, where they also studied such a phenomenon. Um, but under a complementary settings. So in our work, we started this kind of reproducibility where we train our model, different model on the same data set, right? So they did an experiment trying to study training the same model on non-overlapping subset of training data. So the setup is following. So suppose you have a set of A data set, which is S, and you partition the data into non-overlapping subsets. So S1 is a subset of set of A, and S2 is another subset of set of A where they don't have any overlap. Uh, and and then you're going to train your model, the same model, on this kind of a non-ordinary subset, and you do sampling from the same noise and with the same ODE sampler, where n is the number of training samples. And you observe something quite complementary to what we find, is that when n is very small, right, you're going to see something like memorization, right? The nearest neighbor in S1 actually is you are reproducing the nearest neighbor in the training data set. And actually, if you look at the compared images on two non-overlapping subsets, they are very different. The general image are very different. But the interesting thing is that when you increasing the number of training samples to be very large, then the interesting thing is that the two images, the two models, even they are trained with not any overlaps, right? So they're going to generate the same image will start from the same noise. But you compare to the generated images of the two models between the nearest neighbor in S1, S2, you're going to find that actually the generated images will be different from the training data set, right? So this reproducibility even holds when you train on a non-overlapping subsets. And we also did some experiment trying to do some study of how the training data set, the size of training data set is affecting the reproducibility phenomenon. And what we're going to find here is that we're comparing the reproducibility between different models, and we are going to change the size of the training data, where the x-axis, the size of the training data in the log scale, and the y is the reproducibility score. And what we find is that when the model, the training data set is small, you're going to have high reproducibility between different models. And we were increasing the size of training data, the reproducibility diminishes where and it will further increase the size of your training data, then the reproducibility reemerges again. Actually, this reproducibility strongly correlates of how the model is able to generalize. So to measure generalization, we introduce a very naive score where basically what we're going to measure generalization is that like suppose you have a generated sample by a generative model X, and you're going to compare the similarity, the dissimilarity from X to the whole training data set. And inspired by the reproducibility score, we're going to define a generalization score by looking at how different the X is from the whole training data set, right? So when X is very different from any of the training data set, the JL score actually is also a probability measure that will be closer to 1. So when X is closer to any of the training points, then the JL score will be closer to 0, which indicates memorization. And this is a curve under the same setup. I mean, we run the experiment and we show a curve like this. But the interesting thing is that when you put those two curves together, right, under the same setup, you're going to find something interesting, is that the reproducibility and the generalization strongly matches with each other, right? So when the model is memorizing, the model is reproducing to each other, right? On the left-hand side. On the other hand, when this reemergence of reproducibility actually strongly correlates when the model is able to generate new samples, right? So there's a two distinct regimes in training diffusion models. One is pure memorization. Another is generalization, where the model is able to generate new samples, but the model is also reproducing to each other, right? So this leads to a very interesting question is that why this happens and how this kind of a generalization emerges when we're training our diffusion models. And trying to answer this question, we give some theory, simple theory to study this. And if you want to develop a theory, right, first you want to understand why this kind of phenomenon happens. And to understand why this happens, you need to look back to the sampling procedure of your diffusion models, right? If you look at back the backward ODE sampler of your diffusion models, then so the reproducibility basically says that your diffusion models is able to learn the same score function, right? If they are learning the same score function starting from the same noise, this is a sufficient condition that they're going to generate the same image, right? But however, we may know that the model is have a very strong score approximation ability. But why the diffusion models are reproducing in different regimes, right? And the answer, or what I believe, is that the model reproducing in two different regimes is because they are learning the different score functions, or in other words, they are learning different distributions. And you can imagine when the model is reproducing in a memorization regime, where the model is just memorizing the training data without ability to generate new samples, then this is a scenario where the model is learning the empirical distribution of your training data, right? Other words, so this empirical distribution is just a summation of delta functions at the training data points, right? And if your model is learning such a distribution, you are not able to generate new samples. Your model will be just a purely memorizing, right? And that's why in the memorization regime, all models are learning such an empirical distribution. They are not able to generalize. But on the other hand, on the right-hand side, right, the model is able to generalize and they also reproduce. So why this happens? And from the introduction, we conjecture, right? We have a naive explanation is that the empirical distribution, if we have infinite manner of training samples n, gonna to interpolate the true distribution, and that's my. But we know that this will suffer from the cursed dimensionality, right? And in practice, the number of samples you need actually is way smaller than what the worst case theory predicts. So why the generalization happens? So what I believe the generalization happens in training diffusion models with finite number sample or without cursed dimensionality is because we are not learning arbitrary distributions. So the distributions we are learning actually is relatively low dimensional. And there are many existing work that are trying to probe the intrinsic dimension of image dataset with the belief that the images are lying on union or low-dimensional manifold, right? So this is an example from Tom Goldstein's group in 5 years ago, where they developed some techniques based kernelized nearest neighbor to identify the intrinsic dimension, to estimate the intrinsic dimension of all kinds of image data sets. And they found that even on ImageNet, the intrinsic dimension is around a little bit over 40 or 45 something, right? So this is not very, the image distribution are not very, intrinsic dimension is quite low. And so our theory, so based on, we developed a simple theory, and our belief is that the number of samples to enable generalization for diffusion models actually is growing linearly with the intrinsic dimension rather than growing exponentially with the ambient dimension. And this is why we only need a finite number of samples to enable generalization in this case. And to develop a theory, so what we do is that we consider a variant of this score matching formulation. We consider a denoising autoencoder formulation, right? We consider using a neural network to directly predict the clean image from a noisy image xt. And the reason we consider this is because the Tweedie's formula, actually, there's some equivalence between posterior mean estimation and score estimation. And we also evaluate the rank ratio of the Jacobian once we learned the DAE network, right? What we find actually, if you look at the intrinsic dimension of this DAE network, actually they're also very low dimensional. So this is the rank uh, dynamics across different noise levels where the y-axis is a numerical rank of the Jacobian divided by the total dimension, where the x-axis is the different noise levels. And you can see that on even different data set, right, at some intermediate noise level, the intrinsic dimension is the rank ratio is beneath 10 to the minus 2, which means that actually the intrinsic rank of your learned DAE is very low. So and the minimal point actually is reflecting the intrinsic dimension of your data. So based on this setup, we are trying to develop a theory of generalization. But however, because we don't know the underlying distribution of our images, right? Images are lying on low-dimensional manifold, which could have a lot of nonlinearity. It's very hard to characterize. We don't have any ground truth. So that's why actually let's consider a setting where we assume a ground truth, and we assume the ground truth to be the mixture of low-rank Gaussian. So let's assume our data is following a mixture of low-rank Gaussian, where for each Gaussian, so it's not a full-rank Gaussian, it's a degenerate Gaussian, right? So this UI is basically characterizing the is a basis of a subspace, right? This low, mixture low rank Gaussian is essentially can be visualized as a union of subspace model where the data, each Gaussian mode is lying on a low dimensional subspace where UI is capturing the subspace basis and UI is uh, of size d by r. D is ambient dimension, r is intrinsic dimension. So this UI is capturing the low dimensionality of your images. And based on this setup, we're going to generate samples from this mixture low-rank Gaussian, and we're going to train our model based on this the generated samples to see whether our model is able to recover this or learn this mixture low-rank Gaussian distribution. And what we our I mean because the assumption of data is Gaussian, right? Actually, it has very clean analytic forms. We can derive the optimal posterior, which is something looking like this. And based on intuition, let's do a study when k equal to 1. Let's consider there's only one dimensional, only one Gaussian mode, right, where k equal to 1. And we parameterize our neural network something like this, where u is something learnable weights of the model. And we plug this our parameterization of the denoiser back to the DAE formulation. And you can show that actually we're plugging in and taking the expectation. In this case, actually you can show that the problem can be reduced to the classical PCA problem, principal component analysis. So this suggests actually there's a clear phase translation between whether you can able to learn the low-rank Gaussian or not, right? When your number of samples is larger than the intrinsic dimension, you are able to learn the underlying Gaussian mode. But when you don't have enough samples dependent on the intrinsic dimension, you're not able to learn the distribution. And we realize the phase transition, and right, so this is a PCA phase transition, and this is a diffusion models. Actually, they follow each other. And then the remaining question is how can we generalize this when we have arbitrary number of k, right? We have arbitrary number of clusters. And in this setup, we can show that actually training diffusion models in this setup actually is equivalent to subspace clustering, where we have a more number of like clusters. So the idea here is that we're going to parameterize our neural network very similar to the optimal posterior that we showed here. And then we're going to take this parameterization of a neural network back to the training laws of DAE. And then we can show that actually this problem is equivalent to subspace clustering, right? And we know that for subspace clustering, this is also a classical problem. We can show a clear phase transition. How many samples we're going to need to enable learning the subspace basis, such that we can recover the underlying distribution, the mixture Lorentz Gaussian distribution. And again, the dependence will be linearly depending on the intrinsic dimension as well in this setup, right? And this can be confirmed on real when we're training a real nonlinear U-Net-based network on both mixture Gaussian and real data set, where we train our model on all kinds of data set, and we are trying to fit a linear dependence with the number of samples and the intrinsic dimension. And this is a fitting arrow shown here. But when you're fitting with a quadratic dependence, but with n and intrinsic dimension, right? So the curve actually you will encounter a larger fitting arrow, which suggests that actually even on real data set, right, the dependence with intrinsic dimension is round linear. And moreover, this mixture Lorentz Gaussian even is not a very a precise capture of image distributions. Actually, it can approximate image distribution reasonably well. So what we did is that we train diffusion models on all kinds of data sets. So UNet is like we train UNet or all kinds of image data set, and this is the generated images using UNet. And for this mixture Lorentz Gaussian, we're going to parameterize our denoiser, follow the optimal posterior, and we're going to estimate optimal the use using the training data set itself. We're going to approximate just using the training data set to derive an analytical network to do denoising. And we start from the same noise, and this is a comparison of the generated images, right? You can see that for UNet, and compared to our analytical model based on mixture Lorentz Gaussian, the generated images are amnes and fashion amnes is reasonably well approximate what the learned model. And on CFAR and FHQ, right, although the mixture Lorentz Gaussian lose the fine details, but it captures the essential components in the images, right? And this inspires us that actually we can do some manipulation of images, right? If you believe that this mixture, this linear model holds to some extent, right? So, and we know that for each basis of the principal component actually it captures some semantic meanings of your images, and then you can use the principal component to manipulate the images, right? This is an illustration that actually we can use different component to manipulate different attributes of your data. Like for example, the gender, the head, figure, color, etc. Right? We can manipulate the image, the different attributes. And in practice, we're going to not precisely follow this linear model. So what we're going to do in practice is that we're going to use the Jacobian, and then we're going to do an eigendecomposition of the Jacobian to identify the principal component, and then we're going to we can able to do image editing, right? And then we design a method to do localized precise image editing. We can enable all kinds of benign properties when we do editing of images. And moreover, we can also leverage this idea to do watermarking, right? If we know that the Jacobian is low rank, actually we can leverage the large null space of the Jacobian to do watermarking, invisible watermarking of your diffusion models in intermediate noise levels. So I think I'm running out of time. So maybe I'll just spend 3 minutes about the last part about representation. then I will conclude here. So in the last part, this is a more recent work that we just get accept at clear this year. So what we find is that actually training diffusion models, I mean, in this work, we show that actually diffusion models is a very powerful in learning the distributions of our data, right? So when the model is able to learn the distributions, what I believe is that the model is also a very powerful self-supervised learner, right? Uh, and and uh, and that's why actually I think the representation learning and generative modeling under diffusion models are the sides of the same coin, right? If you're able to learn the distribution of your images, then the representation, when we are looking at the bottleneck layer of your autoencoder, of your denoising autoencoder, actually they can serve as a powerful self-supervised learner. And based on this intuition, actually, we started a two-layer nonlinear autoencoder, a denoising autoencoder, and we're going to look at the representation space. We find that the representation space between generalized model and the memorized model are very different. Where when your model is memorizing, the representation actually is very spiky because they are just memorizing the certain instances, then the representation itself will be very spiky. And for the generalized models, actually the representation will be much smoother, right? There's a significant difference between memorized representation and a generalized representation. And the way we show that is that we are looking into assume our data is following this mixture Laurent Gaussian. We consider a two-layer nonlinear like this nonlinear activation, RaLu activation of our denoising autoencoder. And we show that when the data is sufficiently separated in the memorization regime, actually the model is highly over-parameterized. And then the optimal ways for the DE loss, actually the ways will just storing individual training samples. Is xi, x1 to xn are the training samples. And in contrast, when your model is generalizing, typically this is a case where your model is under-parameterized. And optimal ways in comparison is learning the underlying data statistics. And in the Gaussian case, right, the weights will be learning the means and the covariances of your mixture Gaussian distribution. And this is how the model is generalizing. They learn the data statistics and then they are able to generalize, right? In the memorization regime, the weights will just memorizing. The weights is just storing the training samples. And this is an illustration of memorized weights and generalized weights, right? They're learning different type of structures in your data. And that's why actually if you look at representation, because if you look at the memorized samples, right, the memorized samples is just using one column of the optimal weights to reproduce a memorized a training sample, and that's why the representation will be very spiky. And for generalization, because they are using all the data statistics to be represented, and that's why the generalized sample will be much smoother, right? And this enables us to do a memorization detection method. We're going to look at the histogram of the representation between memorization and generalization. And then we can just do a threshold between the representations to do memorization detection in diffusion models. And by using such a very simple techniques, right, we can enable a very high detection rate, which is prompt-free and training-free, which is much more efficient. So I think I'm running out of time, so I just skip all the other parts. And in conclusion, so what we in this talk I showed three things. One is the to understand generalization, right? We showed a unique started from this unique model reproducibility phenomenon and show this transition from memorization to generalization. And in theory, that our belief is that why we can break the curse dimensionality when enable generalization is because we are learning low-dimensional distributions. And finally, I want to highlight there's a strong connection between representation learning and generative modeling. And these are all the key references. Finally, actually, I want to thank all my collaborators on this talk, this work. And also, actually, we gave a tutorial last year at SML. So if you're interested, actually, all the references and slides are there. Thank you so much.
Thank you so much, Qing. It's this was a great talk.
Yeah, thank you.
Perfect. So I know we're just about to the hour, but if folks have questions, we have a few minutes still with Qing, so we can either unmute or you can put it in the chat.
Yes, I had a question about slide 32.
32.
32.
Let me go back. 30. Uh, yes.
Way back. Okay. So here you talk about the reproducibility score and generalization score, and you said they have roughly the same behavior, but really not. I mean, for instance, if you look at unit 128 at 2 to the 13th, that's the lowest point, right? For reproducibility. Look at the red line in the left score in the left graph.
Mm-hmm.
That's the lowest point there for
You mean
reproducibility.
here?
Yeah, look at the red. Yes, yes. Look at the red. The red is down to 0.2, right?
Yes.
But if you look on the right at 2 to the 13th, the generalization is quite high.
Here, right?
Yeah, 0.8. So
Um,
it's really not matching. I mean, it's sort of the same shape, but it's really not matching very well.
yeah, they are not exactly matching. So I think here is that when the model size is larger, it's harder for them to, I mean, you need more samples to enable generalization. So, so here, larger models is more prone to overfitting, right? And then you need more samples. That's why they generalize at a latest compared to the smaller models, like UNet 64 and the 128.
But I guess what it seems to be saying is that the larger data size, it affects reproducibility score and it affects generalization score, but not necessarily. I mean, they're not necessarily synchronized. You see what I mean?
Yeah, they're not exactly synchronized, but if you look at the pattern, I think they're very
Yeah. So I mean,
uh,
the pattern could just be
capture the trend.
a
Yeah.
coincidence. Is what I'm saying. It's,
Um, So I think the reproducibility is basically saying that all the models, the strong reproducibility, saying that all the models are learning the same scores.
yes.
And when you're learning the same scores, but the learning same score doesn't mean that you are able to generalize, right? The generalization and the reproducibility together implies generalization, where your model is reproducing, but they are generating new samples. Then you are in this generalization regime because if you're only reproducing, right, and your model is generating some garbage, then this is not generalization. But
Okay.
when your model is reproducing and they are generating something new, this suggests actually the models actually are captures the reproducibility suggests that the model is capturing something meaningful,
Okay.
and then they are generating something new. Then this is suggests a generalization.
But what this is saying is that reproducibility is not necessary for generalization.
Yeah, this is not necessary because it's not sufficient for generalization.
Well, it's not necessary because you're getting high generalization with low reproducibility around 2 to the 12th or 2 to the 13th.
You mean here? I
Yeah,
think there's a
you're getting low
tradition.
reproducibility but high generalization at those points.
Uh, okay, so I understand. So here, the reason is there's a low reproducibility, but the generation score is not capturing like how good you are generating an image, right? So here it could be generating something garbage, but still you
Okay.
have a very high generalization score.
Okay.
Yeah,
Okay.
so this is not a true reflection of generalization.
Okay. I see. Okay.
It
All right.
just
Thank you.
says that you are generating something very different from your training data set.
Okay.
Yeah.
So that's only a partial representation on
Right,
the.
right.
Okay.
Yeah, I think if you want to define a meaningful generalization score, you need to combine the reproducibility and this generalization score together.
Okay.
Yeah, I think this
Okay.
generalization score we use here have some uh, defects.
Okay.
It's not perfect because it's only measuring uh, the output difference from the training sample.
Okay. All right. Thank you.
Yeah, yeah, thanks. That was a great question.
Maybe we have time just for maybe one quick question.
Yeah, sorry. I had one question maybe related to the previous one, which I think was very interesting. If I remember correctly, the generalization measure is just like measuring different distances between images, right? Like
Right.
differences. And so what I was wondering also related to the again to the previous question is I was expecting, since we are talking about like estimating the score well, right? I could, and I don't have a ground truth, that is basically the problem. Couldn't I take a very large, the largest, let's say, sample size, estimate a very sophisticated um, model for the score, and then use that to generate images onto which I train a smaller model or smaller models of different sizes, right? And then there, because I have at hand a
Yes.
generator.
Yeah, that's a very good question. So you mean basically you want to study generalization, you're going to study in the distribution of student-teacher setting, where the teacher will be serving as a ground truth. Uh,
Yeah, exactly. Because I mean, I was thinking more in like statistical learning sense. Like there are some papers that study like optimality or minimax optimality in like non-parametric estimation of the densities
right.
with diffusion models. And so I can create, let's say, a synthetic data set, and there I know exactly the score, and then I can actually measure basically if I pass the same noise through the true DGP, the true generator that is high quality, and then I compare that with what I pass through the smaller model or the coarser model, then I could actually measure basically like uh,
Yes. Actually,
directly.
we have a paper on this. We have a paper actually
Uh-huh.
studied this under distribution setting. But I haven't talked about in this talk. But we indeed something that you point to is what we consider. Yeah.
Oh, I see. Okay, thanks. I then
Yeah,
I
but
will
I
check.
haven't talked about here. So indeed, I think one of the meaningful setup is this teacher-student setup. You have a ground truth. You use your teacher model as a ground truth, and then you study
Yeah,
distribution of student model and see how the generalization behavior of a student model. But this has some restrictions because you need a teacher model.
yes, of course.
Um,
Yeah,
so what I believe that if you want to study generalization, maybe without ground truth. One thing I believe is maybe you should look at the representation structures. Like if your diffusion model is able to learn the distribution, right, there must be some structures of the representations and leverage the representation structures in your denoising autoencoder itself. Maybe you can design some metric to quantify generalization based on your representations. Yeah, so in practice, without any ground truth, it's very hard to measure
yeah,
generalization.
yeah. Thanks a lot for
Yeah.
the answer. Yeah, very interesting.
Uh, thank thank you for the question, and thank you again, Chin. So I'm gonna stop
Oh,
it here, but I want to please everyone join me in thanking Ching again for the wonderful talk, and we look forward to seeing you all again at the next seminar.
yeah, thank you so much, Ricardo. Yeah, thank you.